Okay. Why EX DX loop starts from 2K to from 2 to KE and HY loop from 1 to KE minus since boundary condition should be valid for both EX and HY. Okay. Yeah, Priyank. So for this, we'll have to look at the code itself. So let me see if we have some code. Okay. So first we'll answer this doubt in which Priyanka has asked why the EX and DX loop start from 2KE and HY loop starts from 1 to KE minus 1. Okay, so the thing is, when we are doing the update equations, you have to make sure that you do not encounter any uh, array index which is not recognizable to the compiler. So in MATLAB, what happens is the array indices start from 1 and similarly if you are doing it in C where the indices start from 0. So if you look at the index, for example, over here, you and we have defined the array from in our case in MATLAB from 1 to KE. So any index which is either 0 or K or refers to KE plus 1 is like it refers to an empty space or a garbage value which is not recognizable to the compiler. So hence we make sure that the loop does not touch that value. So for example, if you look over here, we are running the j from 1 to j minus 1 because over here we have an index j plus 1. So if we run the loop from 1 to je, this at the last at when the j reaches the value of je, this ez will point towards I comma j e plus 1. So j e plus 1 is nothing like nothing is stored over there. So the compiler will throw an error, so we make sure that we do not touch that value. Similarly, for if we look at some other update equation, for example, over here we are running j from 2 to j because we have a j minus 1 over here. So if we run it from 1 to j, for j equal to 1, this particular array position will refer to 0, but MATLAB has nothing at 0 index because the indexing starts from 1. So that is why we are running it from 2 to JE. And so this is only related to the program in which you are writing the code. So not really electromagnetics involved over here. This is the way we are writing the code so that the compiler does not face any issue. Priyanka, I hope that was clear. If you have any follow-up
Yeah,
questions,
yeah.
okay.
I have other question that is related to PML. So in PML, the second equation, the inverse equation, where you have this sigma term in the inverse, and you are taking to the right side, where you are taking the curl, means considering that as curl of E and curl of X. So I think some steps.
Okay.
Can you
Uh,
repeat in that equation?
okay. Let me see if we still have that over here. Okay, it's not there in this slide, so maybe
Yeah, it is from the sixth lecture.
on six lecture. Okay. Okay,
Yeah,
like
the
this
derivation of this middle equation, the derivation of
derivation.
this,
Okay.
yeah, means formulation for the.
Okay, so for this equation, what we do is that since we have this inverse term over here, we take it to the right hand side. That is clear, right? Because
Up,
solving
up
it in
to
the left
this
hand.
part is up to this part is clear. The next slide.
Next
So
slide.
where you are yes.
Okay.
So how this I of hx term integration term is coming, and from where you are getting c naught delta t by delta x term. So
Okay. So let me see. Maybe this. So I think there's a typo over here. There should be a curl of e. Okay, so there's a typo, I believe, because in the update equation you can see there's a curl of e over here, which is missing over here. So there should be this. There should be curl of x probably. Okay, so there's a typo over here, and for the integration part, what is like since this 1 upon j omega is integration in time domain. So first we for an integration for discrete terms is this becomes an integration of this term over here, del ez by del y. And since we need to where we want to program it, we have to discretize it. So for that, we have written it in terms of summation. So the summation is referring to the integration of del Ez by del Y. So del Ez by del Y, we have labeled it as curl of x by del x. So curl of x by del x is the summation and multiplied by delta t. This is the integration thing. And then again there is this coefficient, and this del Ez by del Y is again written as curl of x by del x, and then whole thing is multiplied by c naught. And when we so and after the once we get this equation, then we what we do is we multiply this delta t on the right hand side, so we get this and we take this second hx term on the right hand side, so we get this hx term over here, this delta t into c naught by delta x into this curl of x is missing over here. So that will be the second term over here, and then this c naught into sigma d by epsilon naught, this delta t over here, and then again delta x, we can take it common from over here, and we get that term over here. And we refer to this particular summation of curl of x as I hx. And so IHX is being the summation is being done in a second step. Instead of adding it every time, we have kept one variable which every time the loop is running, it will add the current curly value to that variable. That that variable comes over here. Were you able to follow this?
yes, cleared. Yeah.
Okay. Any other doubt from previous classes? Else we'll start with today's. Okay. Just give me a second. This power is back. I'll switch my setup. Okay, so we'll start with today's lecture. I hope I'm still audible, right?
Yes, you are audible.
Okay. So today will be the last class for this course, and we have covered till 2D FDTD simulations. Today we'll look at some concepts from the 3D simulation. Look at a free space uh, simulation with a dipole antenna in 3D, and mm, as an assignment, you will get the implementation. I'll discuss the implementation of PML 3D, and then writing the code will and the code for the TFSF's formulation, the total field scattered field, will be left as assignment. And within like a week or so, I'll probably share the results. But yeah, uh, since we have already covered so much in FDTD, uh, going through the textbook and implementing it won't be difficult, and it will also help you test your knowledge, that how much understanding you have got through this course. In the last class, we covered the total field and scattered field formulation. So we'll go over it, like briefly discuss it, and then move towards today's part. So in the last class, we saw that some applications require total field and scattered field formulation, but in which uh, we have an object and which is being like on which a plane wave is incident, and we want to see the scattering properties by that object. For example, in simulation of radar cross section and for example, in the far field, the field radiated by an antenna is also approximated to be plane wave. So this simulation of plane wave in a 2D environment, this is simulated using the total field and scattered field formulation. And for this, what we did was we divided the simulation region into total field and scattered field area, where we introduced an incident array which carried the information of the incident electric field and magnetic field, and inside the total field region we calculate the total field, and outside the total field region we calculated the scattered field by subtracting the incident array from the total field. And for in this formulation, what happens is some nodes lie near the boundary of the total field and scattered field, and so these nodes will be updated by the neighboring nodes, which from some and these nodes, some of them will lie inside the total field and some of them will lie outside the total field. So and this might cause some errors, and for that we what we need to do is we have to modify the update equations at for the nodes near the boundary, such that the if they are being updated by a node outside, we have to subtract the scattered field part from the inside, and if they are being if the nodes lie outside, we have to subtract the scattered field part from the total field which of the node lying inside. And to solve this, we saw the update equations for the modified uh, field values at these nodes. So we had discussed all these update equations in the last class, and we also discussed the code and how the code was affected. So all this part was same as before. So where we initialize the field values, the variables required, the PML parameters, updating the PML, the coefficients for the PML. So all this remains same. The changes which happened was in the main part of the code, where where we included the update equations for the incident electric field. So the incident electric field and incident magnetic field, they are 1D, and the total field values will be 2D. So changes for we included the update equations for the incident fields, and we included uh, the update we modified the update equations near the for the field values lying the near for the nodes lying near the boundaries. So For example, this incident D values are be calculated over here, and similarly for the incident HX values are being calculated over here, and the incident HX field being updated over here. So these are the regions where we made the changes, and rest of the update equations remain the same. Now then we were like the whole idea of the total field scattered field formulation was to have some object in the simulation space, and there should be a plane wave in being impinged on this object. So we can also, this object can, you can design it according to you. One of the simpler objects that we studied was for a dielectric cylinder. So for a dielectric cylinder, what we needed was uh, uh, we have we what we need to do is we have to modify the coefficients which carry the information of epsilon and sigma for the uh, for the media inside the media inside the FDTD region. And for that, what we did was we calculated the distance from the center of the cylinder, and check, and if the node lied inside uh, the node lied inside the cylinder region, we updated the coefficient values with the proper epsilon and sigma values. So this was the logic behind the including a dielectric cylinder. So if you just comment this part out of the code, what will happen is the cylinder will vanish, and if you keep this, if you change the radius, then again the cylinder will become bigger, and the coefficients will be modified for longer distances. If you want to use a rectangular or patch over here, for example, if you want a cuboid, all you need to do is run the loop from j to jb minus 1, and uh, check the distance for a square. So we are calculating the distance by using this formula for uh, radially. But if you want to keep a cuboid, you just need to assign the values inside the square, and that will be done. For more complex structures, you'll have to do it more carefully. Now, another issue that lied with the previous formulation was that we were using we were using staircasing. So now, the staircasing is that, for example, if you have a curved surface, it will approximate it using these squares, so which is not very good approximation. So what we need is, if we were able to fill this particular region with an effective permittivity and effective conductivity, this would be better approximation. So we discussed this quite a bit in the last class, that how we divided this particular cell into smaller regions, and for each cell carried a weight, and if it belonged inside the circle, we would add the weight to the permittivity, and if it lied outside, we will not add the weight to the permittivity. So if like, this is pretty much approximation method. So if you go through it, you will understand it. The code is also fairly simple. If you have any doubts, we can discuss this. But I believe this is fairly simple. So this is the result for the. So this is for a norm, the first code that we saw for the cylinder approximation of a cylinder, and this is using the staircasing. So you can see over here that these nodes are like this squarish over here, and over here you can see we have used the approximation. So some cells are filled with some lighter values, like some values in middle of the epsilon and epsilon for air. We also saw the results in the last class for plane wave incident on the electric cylinder. We'll just see it once again. So if you have any confusion, we can discuss about this. Over here, you can see that whatever you saw in this region was only scattered, and inside this region, you were seeing the total field. So I'll just show the code. So how to include the cylinder, just in case if you had some doubts regarding that. So this is the code for the TFSA formulation. We have already gone through this. So from year to year, it this is same. We included the uh, the parameter values and initialize the field and PML region over here. So here is where you include the cylinder. So once you have already defined the GA and GB, these are the coefficients that have to modify. So once you have initialized them with ones and zeros, then you include the code for the modification of the simulation region where you include the cylinder. So you define the radius, epsilon, the conductivity, and the center of the cylinder. And so I've commented this part of the code over here where we have included the cylinder. And then you calculate the distance of every node and check whether it lies inside the radius, and then you modify the um, coefficients according to the permittivity and the conductivity values. So I've commented the staircasing code over here, and over here the uncommented part here is the code for the approximation uh, uh, of the approximation part, the approximation code. So you can see over here we are checking for every smaller cell, and if it lies inside the radius, we are adding its weight to the epsilon and conductivity, and then using that epsilon conductivity, we are updating the coefficient values. So over here, you include the value for the cylinder, and then you again start with your normal, like the previous TFSA formulation code. You update your PML cells, then start with the main part of the code, and rest of the code for the TFSA formulation remains the same. So no changes over here. So only change you needed to do was outside the loop where you included uh, the modification of the GA and GV for this dielectric cylinder. So in the last class, we had one assignment where, uh, where we had to look at the TFSA formulation and inspect each line. I hope everybody was able to go through the code, and if you have any doubts, you can ask now or maybe later through email as well. This is fairly simple, modifying the conductivity and radius and seeing how it affects the code. Then varying the permittivity values. Then this again I've discussed today in today's class about the smooth transition. So we just saw the code, so the how to include the electric cylinder and a smooth transition. And then again the last class, this question was asked: what happens if ABC appears after the update equation for ENH? So yeah, so even I had not tried it. So apparently ABCs, when kept after the update equations for E and S, they do not work, and this probably happens because the H fields are already updated with the values from E fields, and the PML is not able to override the absorption. So when you place them in between, so what happens is the E fields are we since we are applying the PML on the electric fields, so the E field is modified in such a way that they die at the end, and the and this matching thing is then again so this modified E fields is then used for the update equations for H. So if the H fields and E fields are updated, and if the PML is kept after the update equations for E and H, they won't work. So essentially, what will be happening is they will be matching electric fields after the magnetic fields have been calculated, and the magnetic fields will again update the electric fields in such a way that the reflections still happen. So I hope this logic for this was this worked for you as well. Like this is how I'm understanding it. If you have any other explanation for this, I'll be happy to know. Any questions from assignment 3? So I'll just pause over here. And any questions from what we discussed till now from previous class and question as for assignment 3, we can take it now. Otherwise, we'll start with the 3D FDTD, chapter 4 from DM Sullivan. Okay, so I believe no questions there. So we'll start with the module 5 today, and we'll try to cover as much as we can in today's class. And since today is the last class, any questions you have from 3D, today will be the last day that we can interact, like, or otherwise we'll have to follow up on email. So in today's class, we will look at the update equations for 3D in free space, and we'll discuss how to implement PML in 3D. So I'll show. And I'll show the update equations for the free space simulation, and we'll see how to include a dipole antenna in the simulation region as a source. And I'll show the code as well, and then we'll discuss the PML, the and the inclusion of PML will be left as an assignment, and this total field and scattered field and this entire section will be as an left as an assignment for you to study from the textbook. And if you have any doubts, you can reach out to me. So this follow so all these things follow everything from the what we have already gone through that in the previous lectures. Everything is very same as what we have done in 2D. It's just that we have more equations to deal with, more terms to deal with, but the basic formulation remains the same. No new concept over here. Uh, just that we have to do more work because we have more terms. Okay, so we saw the FDTD grid in the 2D, which was formed, which was given by Professor Yi. So we call this Yi cell, and in 3D, so the Yi cell will look something like this. So where you have all the electric field and magnetic field components, Ex, Ey, and Ez, and Hx, Hy, and Hz. So this is what a unit cell of a E looks like. So the H fields are so we have so from by convention we assume that the H fields are being calculated at the center of the faces of the cube, and the E fields are being calculated at the center of the edges of the cube. So for example, this H field will be updated by using the Ey and Ex, and then this Hx will be updated by Ez and Ey, and which you will see up in the equations over here. So we'll start with the again the Maxwell's equation, and so Maxwell's equation for 3 dimension comprises of these many equations. So this is where the all the works like the effort comes in. So all these equations are like of the same format. You've already seen them in 1D and 2D, where you had a time derivative term over here and one spatial derivative term over here in 1D and two spatial derivative term over here in 2D as well. So all these equations are the same template. All you need to do is you have to write separate update equations for all of them. Only the work increases and nothing else. That is how the complexity is increasing in this case. So this is here is the sixth set of update equations for the electric field and magnetic field. Then again we have to you need to calculate the electric field from the electric flux density by using this equation. So I hope this is clear. Uh, for 3D, we have this set of equation, and then you can see as I said, Hx is being updated by using Ey and Ez. So you can see over here, So if you take consider this phase, the hx is being updated by ey and ez. If you take this phase, yeah, the hz is updated by ey and ex. So here you can see hz is being updated by ey and ex. And for electric field, if you see, if you take a phase over here, then ez is being updated by hx and hy. So you can see over here this dz, which will be used to calculate the ez, will be updated by using hy and hx. So this is how you can see from the E cell that which field values will be used to update which field values. Now again, taking the finite differences, I believe everybody is now very comfortable in taking the finite difference approximation. So so on the left hand side we have dz, which is a derivative in time. So taking a time derivative and then this del t will become a delta t, and multiplying it on the right hand side, and then again taking uh, the finite difference for hy and hx in terms of space, you'll get the final this update equation. So this dz term and this dz term divided by this delta t on the left hand side is the finite difference term for the left hand side, and for the right hand side again you have this uh, mu naught epsilon naught and delta x over delta x. You have to uh, take it common from the inside the bracket, and then you have hy again, hy for the first term inside the bracket, and this hx and hx term for the second term inside the bracket. So fairly simple. We have seen this in the for the 2D update equation as well. And similarly for taking the finite difference for for one of the magnetic fields, we see the same trend. So this is already known to us. So I've just shown two examples, one from the for the flux density, another for the electric field, for the magnetic field. And this is how you have to write the update equations for all the six Maxwell's equations. I hope this was clear. If you have any questions, maybe I can stop over here for some time and see if you have any questions. You can take a look. Okay, so it's fairly simple. We have nothing that we have not already seen. Yeah. So we have started with this Maxwell's equation, and we have got the six update equations. And for each update equation, you'll have this will have an update equation for your like compatible with Python, C, or MATLAB, whichever language you are using for this course. So this here is a set of the six update equations that you'll need to write your 3D FDTD code. You can see this dz, this dx is being updated from dx values and hz and hy values. Similarly, dy is being updated from hx and hz values. So you can try on your own writing this. Otherwise, you already have like this is already shared with you. You can use them to write your own code. So any doubts over here? Uh, so this is mostly what you have already done. Um, just take a look. If you find something difficult, we can discuss it. Otherwise, there is nothing new that I need to like teach you. This is already known to you. Again, we have this 0.5 over here because we are following the Quran limit. Um, already seen in the big the starting lectures in the 1D as well, like how we got this 0.5 over here. all the normalizing things, all is done, which you're already familiar with. Again, in one of the doubts that was asked in the beginning of this class by Priyank, that when we are writing the loop, we need, why do we start one particular loop from 2 to JE or IE, and then some of the loops we are starting from 1 to JE minus 1. So again, so you can see over here, this there is a J minus 1 over here, and there's a K minus 1 over here. So while writing the update equation, while writing the loop for this update equation, you have to run the loop from I. The I will be run from 1 to IE, but J will be run from uh, 2 to JE, because there is a J minus 1. So if you run J from 1 to JE, what will happen is this particular term will become 0, and this might throw an error in MATLAB. Similarly, K will be run from 2 to KE, because we need to make sure that this does not go below 1. And this you have to follow in all the update equations. For example, if there is a I minus 1 over here and J minus 1 over here, so this will run from 2 to IE and 2 to JE, but 1 from 1 to KE. So this you need to follow. And since we already have PML working at the boundaries, that will take care of the rest of the things.
Hello.
Okay. Yes.
Yeah. So it will be like three nested loop, then ABC condition, then three nested loop for H, right? So the
Yes. Yes.
process will be like this. Yeah.
Yes. So we'll see the code also. Yeah, so we have a main loop which is running for the time step, and then inside that we will have nested loops for each of this update equation. So there'll be we'll start a loop for uh, I, J, and K, and then update the DX, and then close this loop, and then there will be again another loop for DY, which will where we'll have I, J, and K, and then update equation for DY, and then we'll close this loop. So for each update equation, you will have a separate loop, and this all these update equations loops will be inside one big time step loop.
Okay. Okay. Yeah.
Okay, so now including how to include a source, you can directly keep a Gaussian pulse inside the source and see, uh, and and that is how what we'll use for this dipole antenna. So so I hope everybody is familiar with the like what a dipole antenna is. So a dipole antenna is looks like something like this. So it has two arms, and we give an current voltage. So we give a voltage source over here, and what happens is in one of the cycles this is plus and this is minus, and then another cycle this will become minus and this will become plus, and this is how, and this causes. So, functioning like how a dipole antenna works is relatively uh, not part of this course. So you just need to understand that we have antennas which acts as sources in electromagnetic engineering in general. So an antenna radiates electric and magnetic fields. So the waves are radiated by the antenna. So we are using this dipole antenna as a source for this simulation. And this dipole antenna is made up of this wires. So we have two thin wires, and there is this source in the middle, which gives a potential difference between these two wires. And we already know how to assign like conductors inside the simulation space. You just need to make the conductivity infinite, and that is how you make a metal or the inside the simulation space. And for that, what we do is we make GAZ as 0. So any point where GAZ becomes 0 becomes like act as a PEC. To specify PEC, we make GAZ 0, and that is what we'll do. Outside the loop where for example, like where we specified the relative cylinder. Similarly, over here, what we'll do, we'll make GAZ at 0. So for this entire space, like starting from Kc minus 10 to Kc plus 10, so Kc is basically the center node, and so 10 nodes above this and 10 nodes below this, we are making all the points over on this like line as 0. So this whole thing becomes one big metal wire, and then at the center, what we do is we make it 1, so that there is again free space between these two wires. So this is how we specify a dipole antenna, and then within this point, we will give a electrical source over here. So we could have gone through this process of using using a potential difference to like potential difference to calculate the current, and this using this current to update the H field, and then this H field would have acted on the electric field to act as a source. But instead of going through all this step, we what we do is we directly feed the value to electric field over here. So like how we have done. So we excite a pulse, like we assign this Gaussian source to this pulse variable, and then we assign this pulse variable to dz. So this we have already done. This is just that we are giving this Gaussian pulse in middle of these two wires, which will excite the both the like ends, and will have this particular thing acting as a dipole antenna. I hope this was like okay with you. To learn more about antennas, I think antennas in itself is a very vast course, but you can go through some websites like Everything RF or Microwaves 101. They have small articles written on dipole antenna, which I think will suffice for your knowledge. Or you can go through the textbook by uh, T. A. Balanis, Antenna Theory, which is a really good book on antenna. Like all universities follow it as the standard textbook, so you can use that as well. So I'll stop here and maybe take questions on this dipole antenna thing acting as a source. Okay, so I hope
Uh,
this was clear.
Hello.
Yes, yes, Priyank.
Yeah, so when we are giving the pulse at the center, will it not be extend to the metal side?
So what is happening is when we give the pulse at the center, this the excitation happens in such a way that these wires themselves like act as dipoles, and and this both the like this particular system works as a dipole antenna. So this is like a Gaussian pulse exciting the two arms of the antenna, and then this antenna radiates. So this is how the simulation will function. Like, are you able to follow me? So this
No,
particular
my point
excitation
is,
is exciting the arms of the antenna, and since they are conductors, the all the electric field values will come at the same potential when we give a potential over here.
okay.
Okay, this at first this might look a bit complex. So what you can do is try writing the code and simulating it, and this might become more clear when you try to implement it. What is essentially happening is we're like we're using the same concept which is used in antennas, where we have a source between the two arms and the source excites the arms. Similarly, we are giving an excitation between the two arms, and when we give particular e field value over here, this will excite the both the arms in such a way that this acts as an antenna. So this the whole thing will come at one potential, and this whole thing will come at one potential, and that is how the electric fields will work. And this electric fields will then propagate through like an antenna propagates the E fields. So once we give a source over here, all the E fields will be updated, considering it as metal, and then all the points around these nodes will be updated, considering that this metal is acting at the same potential by this given by this source over here. I hope that was like a bit clearer than what I've said. But again, try running the code. Maybe that will make more sense to you. Or
Yeah.
you can skip this entire thing and just keep one Gaussian source in the middle and see how that radiates. So and
Yes.
this is just an example of having one of these sources. You can try making different structures and seeing how that whole thing happens. So making a dipole antenna was easy, keep it, like just using this two lines of the code. But for example, what if we wanted a horn antenna or a more complex like helical antenna or something like that? So you'll have to write more complex code. Like you'll have, but again, you'll be using the same concepts. You'll have a one excitation near the one the 2 points, like the two metal points of the antennas, and your metal structure will become more complex, but you will be using one point source near the excitation of this antenna.
Okay. Okay. One more thing here on this slide. Is it
Yeah.
DZ or GAZ in the second part?
uh, so this is
DZ
GAZ,
or
this is GAZ,
the
and this
last.
is DZ.
Okay.
this
I
is
thought
this is
like
DZ.
this. Okay. I thought like the center part of this dipole there we are giving the pulse. So this might be GAZ. I thought.
So GAZ specifies the media properties. So we are specifying the dipole which is outside. So this particular part of the code will be outside the main loop, where we have specified the dipole.
Okay. So
This
dipole part is like the material. So
yeah,
this is
yeah,
like
that is material, and it is specified outside the time loop, the main part of the code which we write it as. And
okay.
this source thing is happening inside the time loop, where we are giving this pulse to the electric field value between the two arms of the dipole.
Okay. Okay. Okay.
So once we have specified the electric field value, which is essentially the electric flux value, so interchangeably I'm using the term. So once we have specified the electric field value over here, the update equations will act in such a way that this whole thing acts as a dipole.
Okay.
Yeah, so this part will lie outside the loop, and this will lie inside the loop uh, between the update equations. Once you have updated the dz values, then you specify this dz value, and then you calculate the e field values, and then update the h field values. That's how usually we are writing the code. So this is inside the main part. Okay, so let's take a look at this simulation. So once we had a, dipole antenna over here, so this is how this radiates in the free space. At the center, there was just this dipole antenna, and when we excited it with a Gaussian pulse, so when this wave was like sent out, like propagated from the like it left the antenna and propagated outside. Very similar to excitation of a Gaussian pulse in free space. Now, so taking a look at the code, this is all the same. We have the update, like the the excite, like writing the values for simulation space. We You can see we have added ke over here. So for 3D, we have three dimensions. So I, J, and ke, and then center of the space is given by I by 2, J by 2, and ke by 2. So this is the center of the space where we're specifying the Gaussian pulse. Then again, the permittivity values, the calculation of time steps, and everything, uh, that remains same. Now we have nine field values. These the electric fields, the electric flux, and the magnetic field values. The Gx, Gay, and Gaz refer to the material values. And over here, you can see we have specified the dipole over here. So this is where we specify the dipole. And in case of TFSA formulation, this is the place where you will specify your cylinder or sphere. So over here only you will specify the sphere if when doing the TFSA formulation. And then again, the source over here, uh, this thing for recording the plots that you are generating. You can, if you want to save time, you can turn them off as well. And then you start with the main part of the code. So as we discussed, we have for loop for I, for loop for J, for loop for K, and then finally the update equation over here, and then we close all the loops. So dx is being updated by hz and hy. So this we saw just now. Then again for dy we have the update equation. Dz we have. So for all of them you write the nested loops. Then you define the source pulse value and then give it to the dz. So here is the antenna source, antenna source, and then once you have updated all the electric uh, flux values, you calculate the electric field values from by using the coefficients. So dx, dy, and dz, you are calculating the electric field values. You can see over here, once we had given the this gaz as a 0 for the both the arms. So in both the arms, you will see that this Ez will always be 0. So the Ez will always be 0 in both the arms. And you know the on in like on the PCs, the electric field is 0. Similarly, we write the update equations for the magnetic fields, nested loops for all of them, and we've already seen the update equations. And then for plotting it, there's now this issue is there that since the all the fields are in three dimensions, so visualizing them is an issue. So what we can do is you can take your three-dimensional electric field over here and take one of the planes where you want to see. For example, since if you can your matrix looks like something on this slide, so it has three dimensions, but you cannot see the whole matrix at once. So what you can do is you can take a plane. If you, for example, if this is kc over here, for k equal to kc, you can uh, in MATLAB you can write it like this, or you can, for other languages I think you might have to write a code like a loop over here. So for all the values of x and y, and for k equal to kc, you can store them in a separate variable, which is now a 2D matrix, and you can use this 2D matrix to in SURF or maybe ImageSC to plot to visualize the wave propagation. So visualization is a bit of an issue in for 3D fields, but yeah, so you can do this, and then everything remains the same, like plotting it for making it good and closing your video writer object. So yeah, so this is the like very simple code for 3D FDTD, but we have not used PML over here, so that is why we stopped our simulation before the waves hit the boundaries. We'll look at the PML formulation now, and the writing the code will be left as an assignment. Any questions from the code part? Okay. So coming to PML, the formulation again is the same as the one we did for 2 dimension, but since now we have 3 dimensions, we will have one more term. So if you recall, in for 2 dimensions, the PML formulation for require had these two terms over here, and now since we have 3 dimensions, we have one more term, and in this case, this becomes the inverse term over here, and the right hand side dimension. And so we already have done the formulation where we had these two terms, right? So if you so now we have three terms, and if you recall, when we had this inverse term over here, what we did was we took it on the right hand side, and then we got an equation, and then we evaluated it like that. So then we this all this curl terms came, and this 1 by j term of curl will become the integration. So it follows the same formulation, and so we will just see formulation for one of the update equations, and this and in for 3 dimension, what happens is all the terms will have this three terms over here. So all of them will follow the same template for solution. You can try it on your own. Taking so we had three terms, taking one of them on the right hand side so that the inverse term goes away, and then expanding it, we have this c naught, this one multiplied by this term which we have renamed it as curl of h, and then c naught into this coefficient and this curl of h. So we have two terms, and now we are defining 1 by j omega, and curl of h is idz. So we'll have a separate update equation for this term over here, and writing the so now we are replacing this whole thing as idz over here. So we can write the update equation for this. This is not very difficult now. So for the this equation that we achieved in the previous slide, its update equation is now given by this equation where we have these coefficients over here. So already seen in the for 2D case. For the curl of h, again using the finite difference scheme, we achieve this, and this 1 by j omega will become integration, which will again become summation, and then summation will end up giving update equation like this. So fairly like bit complex and simple, because this you have already seen, and this will once you do it for one of the update equations, you follow the same technique for all the update equations. So it will look like this, and the final update equations that you write inside the code will look something like this. So if you run for all the values and all of fetch I, dz, and dz over here for these three update equations written over here. This is what you do for PML. You can try writing on pen and paper and solving it. This will help you um, get the coefficients. But again, the coefficients you'll have to use the same technique that we did in the 2D, where you instead of use calculating and updating the values for sigma, we directly found out like we used a variable xn, and we weigh the property of xn. So we'll use the same concept again over here as well. So this GI3 and GI2, GJ2, all these things will be updated using the same PML technique that we saw in for 2D, where we had this. If you remember, we had this 0.33 into some term power 0 power cube. So if you recall, we had this term, right? So but you will use the same technique to update this all this G coefficients. Right? I'm not diving deep into this topic over here. You can refer to PM Sullivan. So that textbook has all these things all written over there. You can go through the textbook for more clarity on the update equations. I hope this was clear. Maybe I'll stop over here. So this was the last topic that we're covering in this course. Okay, so we'll discuss this assignment for now, and then we'll take questions. So one of the so I'll share the code for 3D FDTD simulation using dipole antenna. Um, you have to study it. You have to study the code and see what each line is, how each line is working, and then modify it to include PML. For help, refer to the textbook by DM Sullivan. So this is how the book looks. I've been referring to this book for the entire for this whole course. Then once you have already done, things will be fairly simple for TFSA formulation. Same concept that you have done in 2D. Again, you can refer to this textbook. Also, if you want to know more about the like the logic behind the TFSA formulation, if you want to study more text, the other book by David B. Davidson. David B. Davidson has more theory on this particular topic. So three questions. A little, you can consider it as the end term project for this particular course. Uh, in some time, I will also share the code as well, but I'll give you like a week's time at least to try it on your own. Yeah, so today we covered quite a lot, everything from module 5 to 3 dimensional simulation. And yeah, so that is all that we are covering today. we're stopping here. I'll take questions. Otherwise, we'll end today's class. No questions. We'll end today's class.
Anand, still you have to upload, I think, the last lecture.
Yeah, yeah, sorry. So there is some issue with the ISSS website happening. So in the last email, I had shared the links to stream. I hope you were
Okay, okay.
able to open that link, right?
No, I haven't opened the mail. So yeah, I think I will be will do that. Yeah.
So they have reached some cloud limit for the uploads, since they are
Okay, okay,
hosting a lot of courses. They have assured
okay,
that in some time they will resolve this issue. But meanwhile, for this lectures recording as well, I'll share the link. Uh,
okay, okay,
since I have not received any email that people are not able to or like view the, like they're okay. I think they're okay with the stream environment, and they have asked
okay,
me
okay.
not to upload it on YouTube. So maybe if you face any issue on stream, please let me know. I'll then maybe upload it on some other site. Maybe I'll upload it on Google Drive and share the link. Something like that I can try.
No, I just check ISSS. So I was going through the lectures from ISSS. So that's why I asked. Yeah.
Yeah, it's fine.
I will
Okay.
check the
So
mail.
yeah, so
I will check.
yeah, please let me know if you face any issue. So that is
Yeah, sure, sure.
and all the tech. Otherwise, all the files, text files, and like all the slides have been updated on ISSS. The lecture is only the
Yes,
thing which is
yes.
pending, right?
Yeah,
Okay.
yeah.
Yeah,
Okay.
so I'll share again today's lecture as well as MS Stream link. For especially students from IIC who are joining, they can directly view. I've created a channel as well where you can directly stream the videos. So that will be easier for you. But that is for the only the people who have IIC IDs. So, if no more questions for today, so we can end today's class. Yeah, thank you for joining this course. It was great. It was a great experience for me. I hope it was for you as well. In some time, maybe I'll offer another course on this portal again. Uh, but for now, thank you, and all the best for your exams and projects, whichever whatever you will use this course for.
Yeah. Okay. Thank you.
Okay. If no more questions, I'll probably stop the recording.